Hello, welcome. Today we will discuss the general 2 to the power k minus p fractional factorial design. In fact, we have discussed on the fractional factorial design in past few lectures, and being a very important one, we are trying to give you as much as possible on this fractional factorial design. So far what you have seen 2 to the power 3 minus 1, 2 to the power 4 minus 1, 2 to the power 5 minus 1, like 2 to the power 6 minus 2. So many such fractional factorial design, 2 to the power 7 minus 3, such fractional factorial design. So all those things in one word is 2 to the power k minus p fractional factorial design. This lecture you can say the generalization of the previous lectures, and we assume that after going through this lecture you will be able to relate to the previous fractional factorial design lectures, as well as given a fractional factorial design, you will be able to construct the design, you will be able to interpret the results of this design. What are the steps in this case? First step is choosing a design. So, what should be the correct or appropriate fractional factorial design? Choosing a design. Then second one is, once you choose the design, you will run the experiment and get the experimental data. Then you will analyze the design, analyze the experimental data. Okay. And you may find out that there will be situations where even in fractional factorial case also you cannot complete all the 2 to the power k minus p runs in homogeneous condition, single homogeneous condition. Under such situation you require to employ blocking. So, we will give an idea of blocking in 2 to the power k minus p design. So, these three things I expect to complete within 30 to 40 minutes of time, and as most of the basic things are already discussed. So, I will primarily concentrate on the general issues and giving you a generalized kind of things, formula and explanation, so that it will justify the topic of today's lecture. So, by 2 to the power k minus p fractional, we say 1 by 2 to the power p fraction of 2 to the power k design. So, here few important things is that one is number of generators equal to p. Second is number of defining relations, this will be p, that is independent from independent generators, that is number of independent generators, plus 2 to the power p minus 1, these are basically number of generalized interactions, So, what does it mean? Suppose for example, my design is 2 to the power 7 minus 3, then what is p? P equal to 3. So, number of generator will be 3. Okay. And what is the number of defining relation? That will be 3 plus 2 to the power 3 minus 3 minus 1. How much it is? 2 to the power 3, that means 7. Okay. Suppose your case is 2 to the power 6 minus 2, then P equal to 2. So, number of generator will be here 2 and number of defining relations will be here 2 plus 2 to the power 2 minus 2 plus minus 1. So, 2 cancel out, that means 3. Okay. So, you have seen earlier, suppose if you consider this design, P equal to 1, defining relations will be P means 1 plus 2 to the power 1 minus P equal to 1 minus 1. So, this will cancel out. So, it is 1. So, in this manner you have to understand. So, what is the number of generators and number of defining relations. Okay. Now, find that there can be, depending on the situations, depending on the p value fraction, there will be different generators. Okay. So, you have to choose the generators in such a manner that you will get the best alias structure. That means, the minimum alias structure I can tell you for the factors of interest, and this is possible when you go for highest possible resolution. So, that means another one is important one is the resolution. Very important one is resolution, and all of you know that resolution will be understood from the defining relations. And if you suppose you have 7 defining relations, so what is the least number of words, in which relation the number of word is the minimum, that will be your resolution. So, now let us see a case. Let you are interested to construct 2 to the power 6 minus 2 4 resolution 4 design. Okay. So, your example is 2 to the power 6 minus 2 4 design. How do you read it? This is 2 to the power 6 minus 2 resolution 4. So, how do you construct this design? This design you construct, you first start with there are 6 factors A, B, C, D, E and F. So, it should be full factorial into the power 4, to the power 4 means 16. So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So, first you consider 4 factors and develop the basic design. Here it will be minus, plus, 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 minus, plus. Second one minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus, minus, minus, plus, plus. Third one minus, 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 plus, 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 minus, 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 plus, 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 plus. Fourth one minus, 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 plus, 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 plus. Okay. So, you know that is 2 to the power j minus 1 minus followed by plus, and that will repeat. So, that is why it is minus plus one after another, that is 2 minus 2 plus 4 minus 4 plus 8 minus 8 plus. So, that is the basic design. Now, you will create generator. So, you can write down A equal to ABC, E equal to ABC and F equal to, let it be BCD. Okay. So, A, B, C will be these three column sign will be multiplied and you will fill up this column, and for F fill up this column. So, as P equal to 2, here P equal to 2, so you have two generators, this and generator this. Okay. So, what is the defining relation? Defining relation you will get using I equal to, if you multiply this with E, that is A, B, C, E. If you multiply this generator with F, you will get B, C, D, F, and these are independent generator and they are generalized one. You will find out A, B, C, E into B, C, D, F. That means what? What is this value? A, B and C will be cancelled. So, it will be AC, EF. So, that is your defining relations. So, defining relations then equal to I equal to A, B, C, E, B, C, D, F, it is AD. AD, BC is cancelled out, EF. AD, EF. Now, what is the resolution here? We want resolution 4, and you see that in the defining relation the minimum number of words is 4. So, resolution equal to 4. So, that means this is what is chosen here. Now, instead of this, instead of suppose F equal to BCD, if you choose generators like this, E equal to ABC and F equal to ABCD. So, I can say that this is my design 1, this, and here design 2, because you can choose like this. So, it is possible that E will be confounded with ABC, that interaction, F will be confounded with ABCD, that fourth order interactions. Okay. So, under such situation what will happen to I? From here you will get ABCE, from here you will get ABCDF, and generalized one you will get ABCE into ABCDF. What is this? ABC will be squared and it will be I. So, you will get DEF. So, that means your defining relation is ABCE equal to ABCDF equal to DEF. Okay. So, what is the resolution here? In the defining relation, the least number of words is 3 here. So, your resolution is 3 here. Now, given this situation, which one you will prefer? You will prefer the first one because of resolution 4. What is the meaning of resolution 3? What is the meaning of resolution 4? Okay. So, here what happened? Main effects are not aliased with other main effects, but main effects are aliased with two factor interaction effects, and two factor interaction with two factor and higher. Here main effects are not aliased with main effects and two factor interaction effects. It will be aliased with 3 factors. Two factor interactions will be aliased with other two factor interactions here. So, if you employ this, you will not able to uniquely estimate the main effects and two factor interaction effect, considering higher order interaction effects are other higher order interaction effects are negligible. But if I consider third and higher order interaction negligible here, then you are in a position to estimate the main effects, because main effects are not aliased with other main effects and two factor interaction effects. So, as a result, uniquely you will be able to estimate the main effects considering this. So, that is why this is a better design. Okay. So, but many a time what happen, you will find out that only resolution is not sufficient enough. For example, you consider 2 to the power 7 minus 2 resolution 4 design. We are assuming that okay, resolution 4 we fix. Now, under this situation, for resolution 4 case, you see how can you generate the design. So, here how many factors are there? 7 factors. 7 factors. That means A, B, C, D, E, F and G. 4 plus 3, 7 factors. So, what is the design you want to choose? 2 to the power 7 minus 2, 4 resolution design. So, 7 minus 2, what is P? P equal to 2. So, your how many generators you needed? Generators needed is 2. So, as it is 2 to the power 7 minus 2, what is happening? We have 7 factors A, B, C, D, E, F and G. Our design is 2 to the power 7 minus 2, 4 resolution, 2 generators. So, it will be first basic design contains 2 to the power 5 runs. So, A first 5 factors B, C, D and E. What will happen? 1, 2 like this up to 32, your basic design A, B, C, D and E. Now, you have to choose F equal to and G equal to. So, there are plenty of options you can choose. You can it is desirable that this will be at higher order interactions, confounded with higher order interactions. So, 3 and more are considered to be higher order interactions. So, you can generate F by interacting with this ABC or confounding with ABC, G also confounding with BCD. So, that means let us create 3 design. Suppose design A, where E equal is confounded with ABC, not E, F and G with BCD. Okay. Second one, let design B. Design B, you can do it is ABC and ADE. F with ABC, G with ADE. Another design C is basically you can go for 4-way interaction that confounded with 4-way interactions A, B, C, D and A, B, D, E. So, if you choose this design and you find out what is the resolution, choose this design, find out the resolution, choose this design, find out the resolution. All those cases you will be your resolution will be 4. For example, this you have seen, for example, this one you consider. Here I will be A, B, C, D, F, I will be A, B, D, E, G and I will be A, B, C, D, F into A, B, D, E, G. So, A, B will go D will go. So that means C will be there, this, and this. So C, E, F, G. So defining relation is A, B, C, D, F equal to A, B, D, E, G equal to C, E, F, G. So this one is in minimum word defining relation, which is 4. So resolution is 4. So now here also similarly you can prove this is 4, this is 4. Now question is that will all the design gives you the similar results, or you in some cases it is better. So that is what is to be discussed. Now go back to the slides again. You see first design, second design and third design. Here you see that all the defining relations only 4 words, here 2 4 words, 1 5 words, here 2 5 words and 1 4 words. I think here 1 is 6 words in the second one. Now once you know the defining relations, you are in a position to find out the aliases. So using design A, you are going to get these many aliases for 2-factor interaction, assuming that the 3 and higher order interactions are 0. If you go for design B, you are getting little better because here number of aliases for 2-factor interactions are little less. If you go for design C, you see that you are getting much less aliased because CEFG, CFEG and CGEF. Now what happen if we just compare these 3 design with reference to word length, that is the defining relations, as well as with reference to minimum length word. You see that for A it is 4 4 4, length minimum length word is 3, for B it is minimum length word is 2, and for C minimum length word is 1. So 4 is the minimum length word. Now the design which is having the minimum length word, least minimum length word, this is known as minimum aberration design. So this minimum aberration design is the best one. Here A is having the most extensive aliasing and C is having the least aliasing relationships, and C is having the minimum number of length words, least number of minimum length words, and C is the minimum aberration design. Now the advantage of minimum aberration design is minimum aberration design with resolution R ensures minimum number of main effects are aliased with interaction of order R minus 1, and minimum number of 2 OA interaction effects are aliased with interactions of the order R minus 2 and so forth. What does it mean? Our example is 2 to the power 7 minus 2. Okay. So if you see, if you take design C, this is our minimum aberration design. So what is saying that, so what is the resolution? R equal to 4 here. So this says that the image, that main effects aliased with R minus 1 means 4 minus 1 3. In this case the main effect, the minimum number of main effects will be aliased with R minus 1 but 3 third order interactions. Similarly, if you go for the second order interactions, this also R minus 2, that means second order interaction. So minimum number of second order aliased interaction aliased with another second order interaction. So that is what is you will be getting. So that is known as minimum aberration design and very, very important. So essentially what happened, you will see the resolution for choosing a design, and another one is that what is basically the minimum aberration design, MAD. Alias structure plays a significant role, alias structure. Same resolution with different alias structure is possible. So, resolution if it is same, then see the alias structure which is giving the least alias structure, okay. And also finally choose the, in this case finally choose the minimum aberration design. So, here a table is shown where a different kinds of to the power k minus p designs are given, number of factors k. So, it starts from 3 to I think 15, this much it is given, and then what are the possible fractions or fractional factorial that is possible, it is given. For example, if I consider number of factors 7, then you see that the possible fractional factorial is to the power 7 minus 1, that is 7 resolution, to the power 7 minus 2, it is 4 resolution, to the power 7 minus 3 resolution 4, and to the power 7 minus 4 resolution 3. So, resolution 3, 4, 5, 4 and higher resolutions possible. So, if you consider here to the power 15, so this was to the 15 minus 11 resolution 3 with 16 number of runs. So, 15 number of factors with 16 number of runs, it is possible. So, we have 15 factors k equal to 16, 15 and number of runs n equal to 16. So, that means k equal to n minus 1, this type of design is known as saturated design and very popular in screening experiments. Now, how to use this table? I will give you one example. Suppose you have 7 factors of interest and you are interested to estimate the 7 main effects and to get some ideas about the second order interaction effects. Third order and higher order interaction effects are negligible. Let you have process knowledge, you know that this process, the third and higher order interactions for the controllable factors or the factors of interest are negligible. So, then what will be the best fractional factorial design? So, we are saying that resolution 4 will be minimum requirement. The reason is in resolution 4 main effects are not aliased with second order interaction effects, it is aliased with third order interaction effects and second order interaction effects are aliased with other second order interaction effects also. But if you go for resolution 3, what will happen, that minimum main effects are also aliased with second order interaction effects. So, in that case you cannot estimate the 7 main effects uniquely, but if you choose resolution 4 design, you will be in a position to uniquely estimate the 7 main effects and you have some idea about the second order interaction effects, as third and higher order interactions are negligible here. So, then what you will do, the previous table what I have shown, a portion of this table is shown here. So, we will go for number of factors 7 and there are possible what are the resolutions from resolution 4 point of view, 2 options are available, resolution 4 7 minus 2 and 7 minus 3. So, then which one you will choose? If you choose resolution to the power 7 minus 2 4 design, then you require 32 runs. If you choose 7 minus 3 4 resolution 4 design, you require 16 runs. Will 16 runs sufficient? Other way around, 16 runs, the less number of runs is always better from experiment point of view. Will 7 minus 3 4 will give us the minimum requirement? Let us see this. If you go by 7 minus 3 design, then these are the E, F, G, these are the generators and defining relations, there are 1, 2, 3, 4, 7 defining relations. Now, if you using these defining relations, you will be able to find out the alias structures. you see that 7 main effects are aliased with the third order interactions, and the second order interactions are aliased in group 3. Okay. So, you can estimate as third order and higher order interactions are negligible. So, you can estimate A, B, C, D, E, F, G uniquely, considering that the third order interaction effects are 0, and you will see that the alias the interactions are alias second order interaction alias in 3, that means A B, A C, A D, A E and their aliases, some estimates you are getting. So, we can say that this design is satisfactory, because we want to know some amount of information about the second order interactions and full information about the main effects. So, this design is satisfactory. Now, what will happen if you go for 2 to the power 7 minus 2 resolution 4 design? You require 32 runs, and there what will happen, once you find out the structure, alias structure, you will find out what, that many more second order interactions, some better information you will get. But as far as the requirement is concerned here, it is sufficient. Which one is sufficient? 2 to the power 7 minus 3 resolution 4 design sufficient to satisfy our condition. Okay. Now, I will explain that the second part is analysis. Under analysis, you first find out the estimate of effect. So, effect I. So, all of you know this is the contrast I divided by to n, let it be n by 2, or other way you can write 2 into this by n, where n in this case is 2 to the power k minus p. So, another one may be you will be interested to sum square I. So, this will be contrast square, contrast I square divided by n. So, these are the things you require to compute. Okay. So, once you know the effect and the sum square, what will happen? You require some kind of another analysis, which is known as which are the effects that are significant effects. So, what will happen here? You will see that. So, you will estimate the effects to the power k minus p minus 1 and their aliases. So, you will estimate to the power k minus p minus 1 and their aliases. This number of effects you will estimate, and then you want to know which are the effects significant. The concept is you go for probability plot, normal probability plot, which is basically known as half normal, sometimes half normal plot. Half normal means what? That you take the mod value of the effects. Okay. Another method is known as length method, and we have discussed normal probability plot, and we have shown that this is cumulative percentage and this side effect. Then the effects which are basically along this straight line, they are insignificant. There will be some effects here and there which may be significant. So, that is what is our normal probability plot. In the length method, they will give you some this is basically subjective, because depending on the graph. So, what is the distance, that is not, but only thing we are saying that the effects which are away from the straight line, they are significant. But length method, what it will do, it will give you a objective assessment. Okay. So, we are not discussing length method because of paucity of time, but you may go for length method. Okay. Under analysis, another important thing is projectivity. Projectivity. Okay. So, we have discussed about projectivity also. Let us see the slide. Projectivity, if you go for a to the power k minus p fractional factorial design, then this collapses into either a full factorial or a fractional factorial in any subset of R, where R is less than equal to k minus p of the original factors. What does it mean? It means suppose you are basically talking about to the power 7 minus 2 4 design, let it be. So, then what happen, you will find out from here to the power 5 design for some subset of factors and fraction may be 1/2 of to the power 5 design for other subset of factors. If you consider a to the power 7 minus 3 suppose 4 design. So, here what happen, you will get to the power 4 design for some subset of factors and maybe 1/2 into to the power 4 design for some other subset of factors. So, there are two subsets which will get that to the power k minus p, in this case full factorial, and some will be having the fractional of that factorial design. The factors which comprise the defining relations, subset of factor comprising the defining relations, those subsets will not get the full factorial, they will get the fractional one, and the other subsets which is not in the defining relations, they will have these full factorial kind of things. So, collapses into either a full fractional factorial or fractional factorial. So, fractional factorial for subset of factor appearing in the defining relations and full factorial for subset of factors not appearing in the defining relations. So, as we start with this to the power 7 minus 3 4 design. Okay. So, what is the subset of factors, total subset? We require 4 at a time. So, this will give you 35 subsets. If you see the defining relations, you will get that 7 subsets will appear in the defining relations. So, that means 7 subset, those factors, those subsets will have 1 by 2 into to the power 4 fractional design, and other 28, that means equal to 35 minus 7, these have to the power 4 full factorial design, means this will collapse. If you take this many subset to the power 4 that subsets 7 25 8 subsets subsets of 4. So, they will have full to the power 4 factorial design. Okay. So, this is what is given in the slide. You see, if we consider example 4 to the power 7 minus 3 resolution 4 design, number subset of factors is 35. Generators we have seen earlier that we have used ABC, BCD and ACD. Defining relation, you see from these 3 generators you can find out 7 subset of defining relations. So, ABC, BCDF like this create 7 subsets. So, there are another 28 subsets. So, these 7 subsets have half fraction of to the power 4 design and another 28 subsets have full to the power 4 design. Okay. So, the projectivity part is important one. So, that means you are now in a position to know which are the factors having in a lower dimension, in the 4 dimensions have full factorial, and which are the factors in the 4 dimension have half fraction of 2 to the power 4. Okay. Then third one, which is also very important, is blocking. Okay, blocking. So all of you know blocking. As I told you that if you go for 2 to the power even 7 minus, suppose we will take 7 minus or 6 minus 2, let it be 6 minus 2 may be resolution 4 design. So that means you require 2 to the power 4 means 16 runs. So there may be, if each run takes a lot of time, so you may not get that everything, the 16 runs can be completed in one shift. You may require 2 shifts, or the quantity required if it is large. So maybe one batch of raw material will not be able to make it possible. So you require 2 batches of raw materials in. So that means even in fractional factorial design you adopt, you require you may not be able to create the set of homogeneous conditions so that all the experimental runs are possible. So there what you have to do, you require to go for blocking. Okay. So fractional factorials, maybe some of the effects will be confounded with blocks. Okay. So under 2 in 2 to the power 6 minus 16 in case, suppose we require 8 runs per block. Suppose 16 runs we require here, and we require 2 blocks because our capability is 8 per shift or 8 per batches of raw material, or depending on availability of operator is such. So then you see, if we say this one, then this 2 to the power 6 minus 2 resolution 4 design, and you know the design, there will be 2 design generators, there will be 3 defining relations, and you are getting this alias structure. Okay. So in the defining relation A B C E, B C D F and A D M, these 3 subsets which will be having at the 4 factor dimension case, 4 factor case, fractional factorial design, but rest of the your that 4 subsets, they will be having your full factorial design, that means full factorial to the power 4 design. So that is what is the concept. Okay. So now here what happened, so you have to choose the block. So if you see the third order interactions, suppose ABC or ACD, suppose if you choose ABD or any of its aliases to be blocked with the blocking variable, then what will happen, you can create 2 blocks. Suppose if you block ABD, or confound ABD with blocks, then you will be getting this structure. So block 1 will go for this, because you will take ABD plus ABD minus. So from the design you have to find out the ABD column, and then you will be having all minus, then there will be all 8 plus. So this will go to, let it be block 1, and this will go to, let it be block 2. Okay. So that's the way you have done blocking in earlier cases. The same thing, you have to find out the appropriate interactions to be confounded here. In this case, ABD or any of its aliases can be blocked. So absolutely no problem here. So this is what is your concept of blocking here. So in general, the concept of blocking is same, that when there are you have paucity of material to say experiment in homogeneous condition, paucity of operator, paucity of time, you require to block. Block what? You require to have a smaller, a fraction of experiment will be conducted under a certain homogeneous condition, and other fraction in the another homogeneous condition, and in order to get the meaningful results, so you require to confound certain higher order interactions with the blocks, and then choose that which are the experiment to be run in first block, which are the experiment to be run in the second block, or so forth. Okay. So, this is what is our blocking. So, we have discussed very precisely the 2 to the power k minus p fractional factorial design. I said that choosing a design is very important. Here one of the issue is resolution, that is a very important one, that alias structure, and this will ultimately lead to minimum aberrated design. So, this is the best one. The reason is it will give you better alias structure. And then you have effect estimate, you have sum square, that using contrast you do it. Okay. And then do not forget the concept of blocking also, this is also very important. In addition, you must know p number of generators, that number of defining relations, okay, and how to compute resolution. So, these are very important, resolution. And projectivity is another concept which we have discussed here. Projectivity is another concept which we have discussed. This also a very valuable information for experimental design. Thank you very much.